constantly throughout the process of data analysis. The package has been developed to run on all major computing operating systems, including Linux, Mac OS, and Microsoft Windows. Now, here is just a brief overview of the package, the software. Structurally, the program is hierarchically organized into two main windows. They're called panels, the control panel and the display panel. From the panels, there are different modules, and then each module will contain several functional groups and eventually the actual function atoms. Now, the control panel is the front control for the data processing, offers organizing all the functions, and the display panel is for all graphics rendering, 2D micrographs, particle stacks, 3D models, and also statistical data charts plotting. As a user starts a project, intuitively the user can move through the modules from left to the right. First, the spreadsheet is to organize your data, and then go to my graph to annotate, evaluate the quality of your image data, and then maybe evaluate the CTF, contrast transfer function of the images. And then go to particle annotation. Particle package offers both manual screening and computational screening for particle data for single exposure image and the two pair as well. It also has a function for two series, and at the extreme extent, it can be used for tomographic reconstruction. Once the particle stack is in place, user can switch to the next stage for particle classification, ab initio reconstruction, and eventually the structure evaluation. The software also offers various data editors, for example, the particle stack editor, the density map editor, and the PDB display to facilitate the image analysis work. I need to mention that these two windows are very crowded on my presentation desktop, but for any high-resolution monitor or dual monitor display system, these two windows can be easily displayed without any occlusion. Okay, so this is the overview of the architecture of the program. Before I give a live demonstration, I'd like to introduce a unbiased classification function that has been implemented in Particle. First, let's take a quick look at the general data analysis pipeline in 3D single particle reconstruction. First, we have data collection, and then we evaluate the quality of the images, select particles, and perhaps make contrast transfer function determination and correction. Then, next step is to classify the particle frames, and then use the class averages, which contains much higher signal-noise ratio for ab initio structure modeling, either direct common line-based angular reconstitution or tilt pair technique, random quantified tilt. Once we have an initial model, we can apply model refinement, and then at the end, structure validation. So this is a general pipeline of single particle 3D reconstruction. Now, if we take a closer look, for example, the first stage particle annotation, there have been substantial amount of research in this area. And once we have a particle stack, there could be some false positives, which can hopefully can be resolved by the second stage particle classification. And at the other end of this pipeline, the 3D model reconstruction, for ab initio modeling, it heavily relies on the quality of the particle classes. Therefore, the particle package offers a new classification technique, which is unbiased and without requiring any pre-image alignment. So I'm going to introduce this method in the next few minutes. First, let's take a look at the conventional practice in particle classification. I'm using a schematic cartoon drawing to show the basic concept without any noise. This is the original particle stack, and first we align these images, and then apply a pixel-based principal component analysis. At the end, we obtain 3 classes. In this noise-free example, is straightforward, and the result is very reliable. However, in real cryo-EM data, there's a significant amount of noise. The signal-noise ratio is often below 5%. The question is, how can we be certain that alignment is reliable? The answer is no, we don't know. Of course, there have been techniques like self-align without requiring any user-defined reference, basically by sum the image stack and then align images to that image sum. However, there is a conceptual difficulty in this approach, and I can easily give a counterexample. For example, the checkerboard pattern. If you have many of these shifted checkerboard pattern images, the sum will be a constant grid field. Therefore, the self-alignment is still ill-defined. So there's this bias and error in the conventional approach. In order to get rid of this bias, maybe we should skip the alignment altogether. So now I formally introduce the direct particle classification technique, or DPC. The objective is to eliminate altogether image alignment and also remove uncertainty in the resulting number of classes, which is often required in the conventional classification techniques. And also, we would like to have a scoring function to assess the quality of the resulting classes. The DPC algorithm is composed of 3 elements. The first is data expansion via systematic 2D image transformation. After that, particle-centric clustering, and at the end, quality evaluation by a mutual inclusion graph. And I'm going to use the schematic drawing to illustrate the idea. First step, systematic data expansion. We have a raw particle stack. Here, I'm using noise-free examples, but the concept can be directly extended to the real data image. Let's make a systematic rotational transformation for each image. Here, I'm just showing the rotation for every 45 degrees. In the real application, the rotation should achieve pixel precision. For example, if you have a 64 by 64 image and the particle object is 40 pixels in diameter, then the rotation step should be about 3 degrees. And then after rotation extension, we also want to apply the translational expansion. For example, for this particular image, we also generate XY transformed images in all directions. As you might have realized that this expansion is very costly. A quick example, if we apply 2 degree step in rotation and plus minus 20 pixels in translation, then each original particle image will generate about 300,000 copies. If we're talking about 1 gigabyte of original data, now we're looking at 300 terabytes of data. Through rigorous hardware integration and software engineering, I'm going to show you later on that this algorithm has now become computationally tractable. The second step is particle-centric clustering. The idea is this. For each particle image in the original data set, we apply the direct principal component analysis without any registration, because registration has already been taken care of by the data expansion. In the eigenspace, we can identify the neighbors of this seed particle. For instance, a transformed version of this, of particle number 3, agrees with the original particle number 1. And so on and so forth, we produce one class here. Now, we continue to repeat this, focus on the second image. For this image, we can find its neighbors in the expanded data set here, and put them together, we have a second class. As we continue, at the end, we are going to get as many number of classes as the number of original particles. In this process, there's no image alignment. Therefore, it is free of any bias.
You have some of those classes will be more populated than the others? Or?
It could be. It could be, depending on the nature of the data set. For example, if you have preferred orientation, sure, some classes will have a large population. Some others will be very sparse.
And you're aligning against the expanded data set or just the raw data set at this point?
There's no alignment.
I mean
the classification.
The classifying against.
Yes, the principal component analysis is on the expanded data set.
Okay.
On the expanded data set. And then for the final clustering, we only look for clusters around each original particle image. Right. Otherwise, there will be a huge amount of redundancy. Right. And at the end, there are as many number of classes as the number of raw particles. Here, okay, so just a few quick observations. First, each original particle sees its own class. At the same time, each original particle can potentially get into multiple classes. So it has multiple identity, which I'm going to come back and mention this in the occupancy definition in 3D reconstruction. Second, for example, in this simplified case, image number 1 and number 3, the transformed version of these images goes to each other's class. Therefore, they have this mutual agreement. And this mutual agreement can be described by an edge in a graph, which I'm going to explain now. First, a quick comparison between the conventional scheme and the particle-centric direct method. In the conventional scheme, if we have these particles, just schematically, let's say we have two classes for two different expressions. In a particle-centric approach, there are 7 classes centered on each particle. And the mutual agreement, for example, between this image and this image is described by a direct linked edge. So with a mutual inclusion relationship, we can build up a very complex graph. And then how to evaluate the quality of each class? If we take a look at a subgraph centered, for example, this image, it has 4 members. If this graph is complete, so with 5 edges, with 5 vertices, there should be 10 edges. This is a non-directional edge. There will be 10 edges. And in this scenario, there are only 7 existing edges. So we can set a score for this subgraph at 0.7. And this is the score function for the class seeded by this particle. So there is now we have a scoring evaluation. The more dense the edge connection, the better, the more reliable the class is. All right. So this is the basic concept of direct classification. Now let me present to you.
So you have 7 classes, and each of them has a score.
Has a score, yes, yes. And of course, we can come up with an empirical threshold and to weed out the poor classes. Here is a quick example. First, the GROW-EL. The data set is from NRAM at Scripps, a public benchmark. This is a cryo-EM data set. It contains 26,000 particles. Now we're looking at a montage of the raw data. And here I'm showing you a subset of the classes. The particle class average and the raw particle, they are juxtaposed next to each other. For example, for this pair, we know that GROW-EL is a tetradecamer, and the top view, it should have 7-fold symmetry. And here in this example, this image, it's not exactly 7-fold symmetric. It indicates that this particle is slightly tilted either on the grid or in the ice. So this basically shows that the DPC algorithm is sensitive enough to pick out this slight deviation from the 7 fold symmetry. Otherwise, we're going to get 7 equivalent blobs. Similar things here. It's not exactly 7 fold symmetric, but for each domain, it has a clearly defined density. Now, interesting case is this. This is a class average. It is off-centered. Actually, this is the intrinsic property of the particle-centric clustering. This class average is as off-centered as its seed image, because we're only looking for neighbors of around this seed image. There's no extra translation or rotation. In order to compare the result of this DPC with the conventional approach, conceptually it's difficult because for this data set, there are about 20,000 classes. And from the conventional approach, we normally obtain a few hundred classes. So it's hard to make a one-to-one comparison. So the idea is to compare the final reconstruction. The real quality of the final reconstruction is what we really need. So here comes the second example, the 50S ribosome subunit, which is also a public benchmark provided by NRAM. This cryo-EM data set contains 82,000 particles. It is a sizable real data. And on the left, this gold-colored density map is from the DPC classes and reconstructed and then refined with the raw images. On the right is the published benchmark result. I want to mention that in the DPC reconstruction, it uses only about 75% of the particles because the other 25% as classes, they have been eliminated through the pruning because of the low score. And also, in the DPC reconstruction, it has this occupancy weighting. Remember that each original particle image can have multiple identities. So if one image has entered into 3 classes, then at an angular reconstitution, it might receive 3 different orientation assignments. With this, each orientation will be assigned 1/3 of occupancy. So this reconstruction has already included the occupancy weighting. Here, just a central slice through the density volume. And at the bottom, it shows the projections from different views of the complete density maps. The top is from DPC reconstruction. The bottom is from the benchmark model.
So you pick, in this case, you picked 75%, and that's obviously the threshold that you can move up and down.
The threshold is basically, I would recommend 0.5. The completeness score is from 0 to 1.
Okay.
Right, and just empirically, just through testing on several data sets, 0.5 is a good number.
Okay, and how widely things deviate from this map if you play with the threshold? You pick 0.6 or 0.4, the maps will get more noisy, or?
Well, I haven't actually tested a wide range of thresholds. Conceptually, if we raise this to very stringent criteria, then there will be much fewer particle images in reconstruction, and then it becomes more noisier. So it is always a trade-off, right? But for a sizable data set like 82,000 particles, 0.5 is a reliable empirical threshold. Okay. So for this, from the central slice and also the model projection, it shows that the DPC model, the density is tighter and cleaner, which indicates that a larger percentage of images have been properly aligned, assigned the right orientation in the reconstruction. Okay, so that concludes the description of this direct particle classification method. And next, I'm going to give a live demo of the program with the real data. I'm thinking to give 3 examples. First is the visual scripting for high throughput data processing. And the second will be just a quick demonstration of classification, class browsing. And at the end, I'm going to show a function for serial image registration as a direct detector becoming the major source of image recording medium. We are looking at serial images with high frame rate recording, and Particle now offers a function to register these images for further processing. So in this example, there are there are 10 images, micrographs in the project. This is just a quick example. So for say I would like to evaluate the defocus of this of the image recording. The idea is I can let the computer, I can let the software system to learn the procedure over one micrograph, and then it will just repeat the same thing over 10 or 100 or 1,000 images. So the idea is first I would tell the system that I'm going to start a new procedure. And so, for example, pick this one and just open the micrograph. Please be a little bit patient with this notebook computer. On a workstation, it should take just a split of a second, but this is a really old notebook. I hope it runs. This is a 2K by 2K image. Okay, so now the micrograph has been opened, and as you can see that it has rather low image contrast because it contains only about 10 electrons per angstrom square. So next, I'm going to switch to the CTF module and just do a quick power spectrum evaluation. Open this up. Okay. Now, as you can see that we have only a white blob at the center. This is because for the for the image recording, I used a very fine pixel size. It's about 1 angstrom per pixel, and on a 300 kV pattern Krauss microscope. So in order to spread out the power spectrum, the idea is to maybe first bin the image. So I can switch to the image binning and bins by twice. All these steps are being recorded on this video scripting panel editor. Now, after binning, you can see the image contrast becomes better, and of course, the image size now has been reduced by half. If we go back and evaluate the power spectrum, you can see that we see better signal, the amplitude modulation here. Just to have a quick evaluation, maybe we do a rotational average of power spectrum. So this is the rotational average, and we can compare this with theoretical characteristics. The nominal reading of this recording is about 3 micron under defocus. So here is a comparison, and then I would like to define the CTF refinement zone in the Fourier space between 12 angstrom resolution and 40 angstrom resolution. And now this is the fitting zone for the CTF determination. And I will just run this at 300 kV. Oh, by the way, the spherical aberration from this Titan Krauss is it has a CS corrector. So therefore, the CS is very close to 0. The manufacturing number is 0.01. And if we start refinement, it takes just a split second, and we have this defocus at 3.15. Now I can just finish recording and come back to tell the system to run everything by using the same procedure. So now I'm going to demonstrate that. We can also save this script for future use, give it a name, and save it. Just for safety, because of this live demo, I'm going to open up a pre-tested script and demonstrate the idea. Also, because of time constraint, I'm going to demonstrate only on a subset of images. So by doing that, I can just unclick, deactivate some of the images. So in this case, only 4 images are active in the project space. So the visual scripting will run through all these 4 images. So now we can start. Okay. So now it's running on these 4 images, and on a fast computer, it will take just less than 1 minute, but it might take a couple minutes for this notebook. As it's running, I'm going to introduce the next demonstration, which is for serial image registration. On the DVD collector, I have collected a image series in around the same regional interest on the grid. The idea is to use a low dose rate recording, and then hopefully the dose fractioning will give a series of 3D reconstructions, and then through a combination of different models, hopefully we can get a better resolution, and throughout the models that has been severely damaged by the high energy electron beam. So once this visual scripting demonstration is completed, I'm going to show you the serial image registration.
Since it's 11:30 right now, maybe if people have any questions, they should ask me right now.
Sure. Yes. It's almost over.
Yeah, we can extend it by a couple of minutes. It's just for remote people, if they want to ask questions, it would be a good time to do it right now.
Absolutely.
And we'll just continue over the next couple minutes. And, you're welcome to.
Sure.
If you want to.
Yes. Okay. So feel free to dial in your question. And here, the visual scripting has completed. And as you can see, for these 4 images, now we have the CTF images. Okay. So the second demonstration is on the serial image registration. Feel free to interrupt if any questions come in. So here, I'm thinking just to demonstrate this with 1 image series. If I load the original image, it has a really poor contrast.
You mentioned in terms of the computing power, with the setup, you mentioned it's more intensive than the typical alignment. Do we need any special cluster, GPU, et cetera, to run it, or?
I would recommend a combination of a CPU and a GPU. Okay. For the example, the GrowEL and Ph.D. Robinson subunit work, I used a 32-node cluster supported by 4 GPU.
I see.
Right. So, but the algorithm can be adapted to different setups. I mean, then the efficiency just depends on the hardware.
Mm-hmm. Isn't your expansion going to be, especially the translational expansion, isn't that going to be highly sensitive to the size of the particle?
Yes. Of course, in the extreme case, if we have, say, 64 by 64 image frame, the extreme case translation will be like half of the image size, 32 pixels. But of course, if we have a reasonable particle screening algorithm, the particle is more or less centered, then we can reduce this maybe to 20 or 10 pixels, therefore to speed it up. Right. It is a very costly expansion.
And for people, if they want to try to use your application, do you provide any online tutorials or training data sets that try to run?
Yes. For online tutorial, there is a recently documented user manual.
So it's image-analysis.net/em.
Yeah. Yes.
The software right now is available through SB Grid. We have installed it.
Yes, all the SB Grid users can have direct access to this.
If you guys are SB Grid, you can just run it, basically.
So this is a user manual page, and there's also a very small tutorial data set. And for some of these sections, chapters, there's also just a step-by-step instruction how to load the MacGraph, how to run the program. So yes, and so the program website is imageanalysis.net/em, and also it has a static link to the SB Grid.
In terms of the origin of the software, so you started to write it when you were back at Brandeis, right? But is Nico involved at this point? Who's responsible for development?
This is a recent effort in the program development. Yes. So signature I developed at Brandeis. It was for part of the screening, and that package the ownership stays in Brandeis.
The particle is developed mostly at MIT right now.
It is yes, started.
Okay.
That time, yes. Yeah, it started about a year ago.
Okay.
Now let's come back to this serial image registration. So I'm just using two images in a series as one example. Now it is running. The principle is very simple. Basically, it uses pixel intensity for image registration over a sizable area. In this case, it looks for similarity over a 1200 pixel tile, and to maximize the cross correlation between two images. So there's no need for fiducial marks. Yeah, feel free to send in questions. Well, this notebook is crunching out the number.
So how many projects is it? So you said you tested it on a number of data sets. Do people actually use it right now for structure determination? I guess at MIT you guys use it for.
Yes, we use that, and also I know a couple groups in Europe are also using this, and one might be close to a publication for the structure.
Okay. And is the method described, published right now, the article?
It's not yet. It's a work in preparation, and at the same time, the user manual is reasonably complete, so the user can start using it. Okay, so now the two-image registration has completed, and as you can see that this image sum has much stronger signal ratio. this is over only 2 images. And then this image can be used for example, particle annotation. And after that, the particle coordinates can be transferred back to the original individual images for further processing. So this concludes the second demonstration. And the last one I'm thinking to show is just a browsing of the particle classes. So we have this GrowEL data set. This is just a subset of this. And these are the classes. And for example, if we want to, this is a class average. If we want to check the members of this class, we can just load these classes. And as you can see, the first one is the class average, the image sum, and then the members are listed. There are 153 members in this class. Another example, for example, this top view is slightly tilted, and we can examine the members of this class as well. These are the members. It has about 140 images. So in this editor, user can just examine and confirm what the class is, and at the end, the class average images can be passed on for 3D reconstruction. And also, there's capability to output them with original particle images with multiple occupancy, which has been used in the example of the 50S ribosomal subunit case. So this concludes the demonstration, and I'd like to answer any questions you might have.
Okay. Thank you very much.
So this is I'm asked to put on this slide just to
right. The next webinar we have November 1st with Ronan Keegan about CCP4. So this will be announced on the website as well as in the newsletter. Okay. So we've got a number of questions through the seminar. If you guys have any more questions here locally.
Just again on how to run it, you said it's been optimized for GPU?
Combination of CPU, GPU, yes.
Okay. But that, I mean,
it's hardware dependent.
Is it hardware type in mind, or is it fairly generalized? I know it's available for Mac OS, Linux, and Windows.
Right.
Pretty broad.
Right. Well, exactly. I think right now the best optimized version is on Linux. And Mac OS also runs smoothly. For Windows, it runs, but without extensive testing. But I think for research, we just in the field of research, we mainly use Linux clusters and the Mac OS clusters. So for practical matters, I think the program has been tested. Yes. Of course, for graphics card, there's also different vendors, and the one, if you need, I can send you the specific model. I think it's I need to check, look it up. Yes, yeah, it's a Quadro model, and yeah, yeah.
Okay, so any further questions from audience, from remote people? If not, thank you very much, and we'll go to lunch right now and talk more, and then you'll meet a couple local people.
I can show you really quick.
What was it around? I don't know, but it's been like that, you could hear it.
But is it red all the time? Or?